So now let's take a look at this problem. And we have a cube, and that is pivoted at point A. In fact, there's an axis located along one line, at the bottom of the cube. It runs through point A. It actually is perpendicular to the axis to the screen. Okay, so it can flip around point A. It can rotate about this axis passing through point A without any friction. But otherwise, it first sits on a horizontal table. Now, there is a small piece of wax of mass small m, which is fired towards the opposite corner at point B in a horizontal direction with a speed v naught. Okay, and it sticks to point B. And as a result, the cube is going to start to rotate. Now, if the speed v naught is large enough, the block can be knocked over, which means the line AB can be rotated over the vertical direction, which means it will continue to rotate until the cube flicks to the other side. The question is, given all these parameters, okay, what is the minimum speed of v naught such that this piece of wax can barely knock this cube over, which means it can cause the cube to flip around point A, the axis. So let's look at how we solve this problem. Okay, there's an impact and there's a rising rotation process, and the basic idea is that we have to mentally separate these two steps into two separate considerations. The first is the collision. The second is the turning or the rotation about the axis through point A. The reason why we do that is because different conservation laws need to be applied for each step. Step one is the impact. Okay, and in this step, the wax carries some energy, some momentum, some angular momentum. Initially hits point B, and they get stuck together. Now, which conservation law can we apply for the collision? Let's take a look at conservation of mechanical energy, the first conservation law we learned. Is mechanical energy conserved for this collision? Well, the condition, as you know, is that all the forces doing the work must be conservative. And as a result, will be an elastic collision. Is this collision elastic? No, it is not, right? Because in elastic collision, they won't get stuck together. And the force that makes them get stuck together is friction. So you don't have conservation of mechanical energy. This, in fact, is a complete inelastic collision. Okay, so we'll rule out the first conservation law, the conservation of mechanical energy. What about conservation of linear momentum? What's the condition for that? The condition is no external force is present during the collision. Now, the system consists of the wax and this cube, right? And look at external force. Is there an external force? Well, actually there is. It's the supporting force through the pivot point A, right? And that's what pins the cube at point A. This point A of the cube cannot move. If you remove the supporting force from there, as the cube is being struck by this piece of wax, the entire cube is going to slide forward, right? Point A will move. And the external force at point A prevents that from happening, so you don't have conservation of linear momentum either, right? So we're down to the last conservation law, and that is the conservation of angular momentum. Is angular momentum conserved? Well, angular momentum, when you calculate angular momentum, you have to use a certain reference point, the axis. Okay, the condition for that, for the conservation of angular momentum, is that there is no external torque through that axis. Well, is that true? Well, in fact, we know the only external force during the collision is the supporting force at point A. But if we use point A as a reference point for the calculation of angular momentum, whatever force that passes through point A exerts no torque, right? Exerts no torque. So therefore, you don't have any external torque for the collision, and you do satisfy the conservation of angular momentum. So that's why we can apply the conservation of angular momentum to the collision process. So let's do that. Okay, let's write down the first equation for the conservation of angular momentum. we have the initial angular momentum coming in. So let's write down the collision process. That's step 1. Li equals Lf, the conservation of angular momentum. Okay, it's measured at point A. Okay, it has to be measured at point A because there is in fact an external force going through point A, but if you use the external torque at point A, that's 0 because the lever arm of that force is 0. So you have to use point A to apply conservation of angular momentum. Okay, relative to point A, what is the angular momentum of the system before the collision? Well, the only moving part was the piece of wax, and it moves at a speed v0, and the line of the velocity v0 is a distance a from point A. Therefore, the L initial is just m v0 a. Okay, and after the collision, the wax and the cube get stuck together, and their combined angular momentum is IA omega, and that IA is the rotational inertia of point A with that piece of wax already stuck at corner B. Okay, we're going to talk about how to calculate IA later, but here's our first equation, right? The conservation of angular momentum. Now, once the collision is over, they start to rise. Okay? The piece of wax stuck at point B and the cube just to rise together. What conservation law can we use here for the rising process? Well, obviously, you can no longer use conservation of angular momentum anymore, because during the rising process, the gravitational force exerted on both the piece of wax and the clay will provide external torque at point A. Okay, also you cannot use conservation of linear momentum for the same reason, because there is an external force at point A. As a matter of fact, as it rises, it will gradually slow down, so it's going to lose angular momentum, and it's also going to lose linear momentum. So we're down to one last possibility to calculate the conservation of mechanical energy. Is that conserved? Well, the only thing that prevented conservation of mechanical energy during the collision was the force between the wax and the cube, and that's what slows down the wax and speeds up the cube, right? That's friction, but they're moving together, so that's not a problem anymore, right? And there's no friction through the axis, as we mentioned in a problem statement. So therefore, you do have conservation of mechanical energy. And so what happens is that initially you have a lot of kinetic energy, 1/2 I omega squared. And after, as it starts to rise, it slows down. So the kinetic energy is gradually reduced and turns into what? It turns into potential energy, gravitational potential energy. Okay. And to flip over, the line AB has to reach the vertical position, as you see in the second diagram. Now, at that point, maybe the thing is still moving. It's still, it is still rotating, but that would require a greater initial speed V0. If you're looking for the minimum possible value of initial V0, then you want to look at the situation where once the line AB becomes vertical, the cube has stopped rotating, which means it is barely able to reach that point. Of course, once it reaches that point, gravity will pull it down by itself, so you don't have to worry about it anymore. So therefore, we can apply the conservation of mechanical energy for the rising process. That's step 2. And to find minimum V0, again, we set the final kinetic energy to be 0 when AB becomes vertical. Okay, so that's the idea. So rising. That's step 2. You can use the conservation of mechanical energy. And then the initial mechanical energy is 1/2 I omega squared, IA omega squared. Okay, the final mechanical energy becomes totally potential in nature, because we set the final initial, the final omega to be 0. So that is equal to mg delta h1. Delta h1 is the height gained by the piece of wax, plus big M g delta H2. Delta H2 is height gained by the center of mass of the cube. Okay, so that's equation number 2. Okay, now let's find what IA is, what delta H1 is, what delta H2 is. Okay, so here we set omega final equals 0 for minimum value of V naught, as we explained. Okay, so there's no final kinetic energy in equation number 2 on the right hand side. So what is IA? Let's see. What is IA? Okay, IA is the combined value of the rotational inertia at point A of the wax and the cube together. Now, for the wax, once it reaches point B, it is a distance AB away from point A, right? So what is the line AB equal to? The length of that equals to square root of 2 times A, right? It's a cube of side length A, right? So for the contribution from the piece of wax, you have small m times the square root of 2A and then squared. Okay, now for the cube about point A, we use the parallel axis theorem. We first find the rotational inertia of the cube at the center of mass, point O. Now that is not an easy calculation, not an easy calculation. Now we gave that to you. It is 1/6 ma squared, as you can see from here. Okay, so that is given. We don't want to start from scratch to calculate that. 1/6 big M a squared, then plus what? md squared. D is the distance between point O, the center of mass, and point A. And that distance, as you know, is half of the square root of 2A, right? Because the diagonal equals the square root of 2A, and therefore that distance is half of that. So it is equal to A over the square root of 2. You square that, and you multiply by the mass of the block. Okay, and that'll give you the answer of 2ma squared plus 2 over 3 big M a squared. So that is how you calculate rotational inertia. Okay, now what about delta H1, delta H2? Well, both the cube and the block sitting at corner B, they both rotate about point A. They're both doing circular motion, but about a different radius, right? For the block, it starts at the initial position of point B and ends up at the final position of point B. And point B initially sits a distance A above the table, and at the end it sits a distance of square root of 2AB. Square root of 2A from the table. Let me explain to you what I mean by that. Okay, this distance, that's the final height of the piece of wax above the table, right? And that is square root of 2 times A, isn't it? The diagonal, right? But initially, that distance is A above. And so therefore, as far as delta H1 is concerned, that's the height gained by the piece of wax. That is equal to the square root of 2A minus A. Okay. Now, as far as the center of mass of the cube is concerned, it starts from initial position, which is here, and ends up there, right? And you know, it also rotates about point A, but with half the radius, right? Because point O is halfway to A compared with point B. So therefore, delta H2 is just half of delta H1. Okay, so now you have all the missing pieces, IA, delta H1, delta H2. And when you plug that into equation number 1 and number 2, you can solve for V naught now. There are two unknowns, V naught and omega. You can go ahead and solve for both of them, or just one of them, V naught, is that's what we're looking for. So V naught equals to whatever. The algebra is a little messy, but if you can check for yourself, if big mass and small mass equal, that makes the algebra simpler. You can find the final answer to be the square root of 8, and then square root of 2 minus 1, and then g, and then a. Okay, you can check the algebra. But that's less important. What's important is the basic physics. So let me go over the basic physics again. You need to mentally separate this process into 2 steps. Step number 1, the block, the wax comes and hit the block, and the momentum is, only angular momentum is conserved. And next, the entire thing rises. It rotates about point A, and that is when you have conservation of mechanical energy. And to find a minimum value of V naught, to barely knock the block over, you just want to make sure that when the line AB becomes vertical, okay, the block loses all of its kinetic energy, stops moving. Okay, so that is a classic problem involving the conservation of angular momentum and other conservation laws combined.